So, good day, everybody. Welcome to today's lecture. Um, Today, we're going to continue by introducing a few additional basic terms that we need in molecular physics. So, last time we were speaking about spectroscopy. We were talking about the Fabry-Perot interferometer as one of the basic ingredients that we need to do spectroscopy, high resolution spectroscopy. And today we will continue. We will see an interesting, not so recent anymore, application, namely the laser that revolutionized molecular spectroscopy decades ago. So that's the outlook or the plan for today. I hope, let me see, so this is recording. First thing is, as usual, I'm going to switch to screen mode. Okay, right, so can you see the screen and can you see the slide number 22? Right, thank you very much. Okay. Last time I realized that my camera did not work in the recording, but I think you could see me during the lecture, right? Or yeah? Okay, that was weird. I hope today it will be better, because sometimes I'm using my hands to explain stuff, so it would be good to have also the camera working. All right, so let's get going. Today we are talking about the laser as an important tool, ingredient in molecular spectroscopy, and it is linked to what we've heard before, in a sense that one of its basic functional units is a Fabry-Perot interferometer. So here on slide 23, let me see if I can make this a bit. So, okay. So one of the three functional units is the Fabry-Perot interferometer. Let's have a closer look. We have a resonator. In between these two mirrors of the resonator, we have some active medium, which could be anything. There are types that are using a gas cell, it could be a liquid, and it could be some bulk object. That was actually the very beginning of laser development. So the first laser system in the 60s was a ruby-based laser. So you take corundum, the precious stone, with chromium ions in it, giving it this beautiful red color, ruby. And you can use now these chromium ions that are embedded in this matrix to do some interesting type of excitation. So the idea of the laser system is the following. We would like to have a population inversion between two levels in some system that allows electronic excitations. For example, chromium ions in this lattice of the corundum crystal. We have, for a basic understanding, at two levels where we do an excitation from a lower level to some excited level. Actually, a two-level system won't work for what we are going to create, namely this inversion, meaning that we have more atoms in an excited state than in the actual ground state, right? So if light comes in, it causes an excitation, and we can think of electrons swapping orbitals going into some electronically excited state. And in this excited state, there will be some lifetime, and then this system will relax, and in this relaxation process send out a photon of the same energy that was needed for the excitation, right? So this is the process called spontaneous emission of light. Now, we don't want to have spontaneous emission. Instead, we would like to have induced emission, which means that if you have some molecular or atomic system in an electronically excited state and another photon comes in, then this other photon, when hitting your molecular or atomic system, will create a relaxation process in a sense that the photon that is emitted has the same energy, obviously, as the incoming photon, because we have these discrete energy levels. Otherwise, we wouldn't have resonance. This is one thing. So we have the same energy, meaning same frequency or wavelength. But we also have the effect that both photons, the incoming and this induced emitted photon, have a fixed phase relationship to each other. So we have coherent light. And that's what makes the laser so interesting, because you have photons, all of them in same and at the same frequency. So you have this equivalence in terms of energy. It's monochromatic, but it also has this coherence, meaning that you can think of a whole beam of photons when coming towards you, for example, as a very good, in a very good approximation, a plane wave approaching you, because all these photons have a locked phase. They are in the same phase relation to each other and behave as this wave, that's single wave that's coming towards you. So in order to get this inversion state, we have to create a very high intensity, meaning we have to create a lot of photons in a given energy range. So to have a lot of possible photons that can be emitted by the medium in your laser system sort of focused. You want to have a small energy area where most of your spectrum is concentrated. So therefore you need wavelength selective elements. And one of these wavelength selective elements is your Fabry-Perot interferometer by itself. So you put the whole active medium in between the two mirrors of your interferometer, which introduces automatically this wavelength selectivity. And it is a Fabry-Perot interferometer with a distance in the range of a meter or something. So we have a very, very high resolution. So we are very selective here. We have one mirror fully reflective and the other one is partially reflective, because here you want to couple out some portion of the light. So on one hand, you keep light inside, and it is reflected back and forth, back and forth. You bring in new photons through some energy source that could be in the early days. It was a flashlight lamp wrapped around the ruby crystal and emitting photons in a certain spectral area or in a spectral range that is useful for absorption inside the crystal, right? But then this light is not a monochromatic light at first, right? So you give you have some source of light that has a certain spectral distribution, and with your wavelength selective elements and the active medium, you can concentrate all this energy that you bring in a small range of frequency, because what you want to do is you want to depopulate all those other excitations or possible energy levels that could be excited, and have only one specific resonance that is supported by your wavelength selective elements. And then you have this avalanche effect, because through this induced emission, a photon that hits an already excited level will cause this induced emission with the photon that is emitted in the process of relaxation being coherent in terms of this phase relation to the incoming photon. So they are multiplying. You bring in new energy through this external system, a flashlight, or typically what's nowadays used in a laboratory is a certain laser that gives you a lot of energy per time. So it has a certain output power and is adjusted to the adsorption spectrum of your active medium. So you bring in the energy for your laser that you are building through another laser. That sounds at first weird, but the idea is that you have a pump laser to bring in the energy, and the actual laser on your table, for example, is the tunable piece. So here you can change parameters to tune your laser through a certain range, because if we're doing spectroscopy, we'd like to go and cover a large fraction of the electromagnetic spectrum, and therefore an adjustable system is what you need. You would like to have something where you can change the mirror distances to change wavelength selective elements, and then you can place other types of wavelength filters into your resonator in order to improve or in order to adjust it to your chosen active medium, right? So you could choose different types of crystals if it's a solid state system, or which was and still is very common, is using a laser medium that's actually a liquid that you mixed yourself. So you have some dye and you mix it with some solvent in it's like a cooking recipe, and you mix 2 or 3 liquids, types of alcohol, to get a suitable viscosity and the refractive index, and you add the dye to the system to get some liquid substance of a certain color, which has the adsorption and fluorescence qualities that you are looking for. So to sum up, we have these 3 pieces. We have the resonator, we have the active medium, and we have the energy source that forms this laser. What's the basic principle? We would like to have population inversion, meaning that we would like to have more of our atomic systems in this active medium in an excited state compared to having them in the ground state, because we don't want to have, we would like to have all possible systems, atomic systems, excited into this upper level, so that we have induced emission as the process that's actually happening whenever a photon comes in and hits the active medium. Okay, so that's the idea, population inversion. I said that we were talking about two niveaus or 2 levels in this system. To explain, we excite and then we relax, and what is emitted in this relaxation process is the light that we are going to use to have our laser system working. But actually, if it's just 2 levels, you cannot have population inversion. You'll have to have at least 1 level more to park your excited state, basically to park your excitation somewhere, and have a relaxation then from this 3rd level to the actual laser level, right? So you would like to have a level that is sort of metastable. Typically, this is a level where any type of alternative dissociation directly to the ground state is not allowed, right? So it's not possible you excite it in a state where it can't directly go back to the ground state. Instead, it has to go to this lasering level, and from there makes the relaxation if another photon comes in and induces this emission of another photon. That's the idea. This is how you get this inversion, actually. So you need another, at least 1 more level to park your excitation. Then you have some preliminary relaxation to the laser level, and then from the laser level back to the ground state, for example, would be a way to have laser emission. Okay.
The trapped parts of our emitted light, meaning the ones that the Fabry barometer doesn't let out, what happens with that? Is it still continue to be reflected between these 2 mirrors, or is it again absorbed by the active medium to create new excitations inside? What happens with the part that's not encoupled?
Right. There is a good question. The idea is to remove all possible alternative ways that can be used to absorb photons. And this is basically happening automatically through the selection of turning more and more photons into those types of photons that are only in resonance with your laser level. Okay, so you have a certain energy difference between the ground state and the excited state. This is the wavelength, or defines the wavelength where you're lasering. And the idea is to have all of the photons that are eventually in this beam that you are creating, or in this loop that you're creating, depending on how the laser is built, all of them are having a wavelength exactly corresponding to this specific excitation. And the alternative ways, they are depopulated because they are through the wavelength selective elements and elements that increase, for example, the absorption for some other frequencies. They are kept low so that you create this avalanche of specific photons on this laser level at the cost of all the other possible ways of how this material that you're using could produce light, right? So, of course, if you give photons of a certain energy to the system, so you put energy into this piece of matter, you will have some fluorescent spectrum. It's a broad spectrum, and your dye that you are using in case of a liquid laser system, this dye that you're using is preferably something that has a very broad fluorescent spectrum, because then by tuning your laser, meaning by changing the distance between the mirror, you can shift the condition for lasering in a certain range of frequency or wavelength, as long as it is within the fluorescent spectrum of your medium, right? So your medium offers a lot of possibilities of how to create photons, and by building the environment, meaning choosing the mirrors and the wavelength selective elements in a certain way, you can enforce that only a certain type of photon, namely one that fits exactly this level that you're interested in, is in this avalanche process multiplied. So you have basically only this type of photon eventually in your resonator. All the others have died out over time, and you have only this single monochromatic type of light in your resonator, because this is the only photons that you're offering multiple times through the reflection on your mirror walls, and that's eventually everything that remains as an electric field in the active medium in order to trigger this induced type of emission and creating even more photons of only this type.
But I thought the ones that we want are the ones that are coupled out of my resonator at some point. I thought that we choose the distance like that exactly these one can pass through and are not reflected inside again.
So this is so you want to couple out some percentage of this energy, and this energy that you couple out is going through, for example, here the mirror on the right hand side, which has a certain transparency. So you take some fraction out of the system, but you can't take everything out, because you need to have this effect of induced population or population, to have the effect of population inversion to be present in your active medium. So you need a certain amount of photons circulating between or going back and forth between your resonator walls, right? But you can take out some energy. And this is the thing now we will see. I'll show you a couple of videos in replacement for a lab tour or for showing this in the lecture. It's also easier because the laser has a certain danger to it, because it's typically pretty high intensity, and reflections might be a problem if you get it into the eye and whatnot. So I think the video is in this sense the safer option, but there will be a chance for you, of course, in the course of other lectures. For example, I'd like to mention Professor Koch and Professor Krenn or Dr. Lackner here, who are experts in this field of laser physics, or Professor Schulze. And in these labs, you can get an impression of how these devices are actually used and how it looks like. But I'll show you in a few minutes a video to introduce you to a couple of standard devices as they are used. Now, on this slide here, you can see some of these, or a standard case, some dye as it is used in a laser setup. So this is a laser setup where we have a liquid. We take, in this case, the rhodamine dye molecule. And if you look at these graphics here, you can see basically its absorption spectrum, absorption as a function of wavelength, and the fluorescence spectrum. See, another peak, meaning that if you provide light of wavelength range between, say, this is maybe 460 to 580 nanometers, then you can cause excitation in this molecule, and the molecule itself then relaxates, and in this relaxation process sends out the photon, which we call a fluorescence photon. And this creates a certain spectrum because there are many possibilities, and you can see the fluorescence spectrum is also a broad spectrum ranging from, say, 500 to about 700 nanometers. So it's almost the whole visible spectrum that we have now access to through this molecular dye. However, only in a certain range of wavelength you have a sufficient high intensity in terms of fluorescence, right? So this is where you can work and try to create a laser by introducing now your wavelength selective tools to cut out some fraction of this broad fluorescence spectrum that your molecule offers. One thing that you see is that the absorption, so the absorption spectrum is at the lower wavelength, so it is at higher energy, and fluorescence is at a slightly lower energy, which can be explained with some basic concepts of molecular physics. And here I'll probably take you quickly to my board here. I'm stopping to share my screen, and I'll take you with me for a moment to the board here in my room. Let's see if this is working. Okay, can you see the board? All right. So, just as a basic introduction to theoretical molecular physics on a system that's very small, namely just a diatomic molecule. So we have two atoms bound to each other at a certain equilibrium distance. Equilibrium distance, I write it as R equilibrium. Now, if we look at the energy, electronic energy of the system as a function of the internuclear distance R, we get a potential energy surface. And I'll draw this ground state potential energy surface.
Can I quickly interject? Because I'm having trouble, how can you enlarge one of the videos? Because I only see you very small. Can someone help me out there?
Which
I can see
on the right top corner. On the right top corner is a button with layout. Then you go to, I think, face, and then you can double click the corresponding video in the button, and then you enlarge it.
Yeah, thank you.
Thank you. Okay, so energy as a function of distance gives you in the electronic ground state a potential that typically looks like this. You've heard about this probably in the past. We will go into this in more detail. It's related to potentials like the Lennard-Jones potential or the Morse potential. So we will talk about this a little bit later in the year. But obviously it has to look somehow like this. We have some minimum at the given equilibrium distance between these two atoms. So this would be R equilibrium, right? So this is what we call a potential energy surface. It's the energy as a function of your coordinates that change the geometry of your molecule. In the case of a diatomic, the only coordinate that's relevant is the distance between the two atoms. So it's a one-dimensional surface, which is a curve, right? So it's energy as a function plotted as a curve. And now if you plot a second state, an electronically excited state, it would look similar to this one, but obviously higher in energy, and probably also its actual shape has changed a bit because it's a different electronic state. You have taken an electron, put it into different orbitals, so your electron density distribution has changed, and therefore the energy as a function of the internuclear distance will also behave slightly differently compared to how it's behaving in the ground state. So I write here a ground state, I give it a G, and then I have some second state, which I call the excited state. So this is an electronically excited state. And same thing, electronic energy plotted as a function of the two nuclei. And as an alternative degree of freedom that we haven't talked about yet, we have to think about the motion that the atoms can perform. So what could you think of? What is this molecule able to do besides being able to get excited through a photon from one electronic state to another electronic state? How
Basically, you have vibrations and rotations also.
Exactly, right. So these are the two. Which one is closer in terms of energy to the electronic excitation?
I think vibrational is
exactly right.
likely.
So this is the next energetic. It's lower in energy than the electronic excitation, but higher than the rotational energy levels. And we can use this simplified picture here, this mapping of energy as a function of distance, also to indicate where vibrational energies would sit, right? I'll do this here for the ground state and draw a few vibrational excitations in this electronic ground state. I can also immediately estimate how the nuclear wave function would look like for these types of vibrational excitations, because if you look at this potential here, it reminds you of something, which potential would be a obvious approximation, a reasonable approximation for low-lying vibrations.
A quadratic potential?
Quadratic, right? A harmonic approximation. So we can say that for small changes in the internuclear distance, we have a quantum harmonic oscillator, and we know how to solve the Schrödinger equation for a particle in such a potential. We obtain a certain type of special function. Does anybody know which type of functions are the solutions of the Schrödinger equation in the harmonic potential?
Some Gauss wave functions.
It's a Gauss in the ground state, exactly. This is what's
Hermite polynomis.
Hermite polynomis.
Hermite polynomials, right? It's the Hermite polynomials. And the zeroth state is indeed a Gaussian function. So if we plot it, it would look like this. And then if I plot the wave function, I'm just indicating the first excited state would look like this. But it's better not to plot the wave function and instead plot right away the square of the wave function, which is our probability of finding the core at some position here. So I think I have to clarify a little bit. In this potential picture where I say I have a particle moving in this potential, I have already made a transformation in the mathematical sense from a system of two masses connected by a spring, for example, right, into a representative system with a reduced mass where I have just one mass moving in some potential. So you can always make this transformation through a coordinate transformation and end up with this picture of a particle in a potential, but it actually means that we have a certain change of distance between two particles, and look at how this system can be excited in terms of vibration. So thinking of this particle in the potential, we would see the ground state has this Gaussian shape, and then the first excited state has these two peaks, and so it continues. We can also see we have a non-vanishing probability to find this particle also outside of the potential, a typical quantum phenomenon. And if it was a perfect harmonic oscillator, these energy levels would have a certain property. Which one?
They are equidistant.
They would be equidistant, right? And here you can see already that we are strongly deviating from the harmonic approximation for higher vibrational excitations. This is called anharmonicity and plays a role, an important role in computational treatments of these molecules, because anharmonicities allow for couplings between modes and those things that allow energy to flow from one excitation in a certain vibration into another type of vibration. Because here we are just talking about a single degree of freedom, because a diatomic molecule only has 1 degree of freedom for vibration, right? So there is no other type of vibrational excitation. But if you add more and more atoms, there are many ways of how the system can vibrate, and we will treat them in a approximation as a product of harmonic oscillators. But due to this anharmonicity, there's also a coupling between them. But we'll get to this later. Now, what's the point of giving you all this stuff right now? I just want you to realize something that explains the fluorescence, so the adsorption and the fluorescence spectrum of this rhodamine molecule that I've just introduced you to in terms of laser physics when you make this dye. So we do the same now for the excited state. Typically, excited states are at have their equilibrium distance somewhere further apart. This is not it's a rule of thumb. It's not always true, because anything can happen when you do an electronic excitation. And if you think about electrons having the effect of compensating the repulsive Coulomb interaction between the two nuclei, then any type of excitation that removes electrons from the space basically between the two ions will actually increase the repulsion part and therefore increase or elongate the molecule. But those excitations where you concentrate more electrons in between would support a stronger bonding, for example, right? So anything could happen, but in tendency, excited states very often at longer distance. And so there is another principle that's now interesting. If I look at the vibrational states in this excited state, they are called vibronic states, okay? Vibration and electronic, vibronic. All right. And we plot a few of these vibrational states in the electronically excited state. Will also look somehow like this. And in order to get now excitations between these two levels, you will have to compare the probability of finding the system in some vibrational state with some distance to distances in the excited states and the probability of finding the system in the electronically excited state at some position. So let's take a different color. Here in the ground state, we have maybe reasonable overlap, no overlap with this vibrational ground state, but there is some overlap with the second excited state in the electronically excited state, right? So you would excite here into this state. This is where you adsorb the light. And then what happens is in the liquid, you will have some non-radiative transmission processes where you reduce the energy through collisions and so on. And the system goes down in a non-radiative decay towards its vibrational ground state. Okay, so we go from here to here, all the way down till you're in the vibrational ground state of the excited state. And now if you compare where the vibrational ground state in the electronically excited state has its highest probability of being located in terms of interatomic distance, this has very good overlap with this type of vibrational excitation in the electronic ground state. And if you compare now the length, this is adsorption, and this would be fluorescence. And you see adsorption, more energy, so we are in the blue or we are on the short wavelength side of the spectrum. And for the fluorescence, we're on the red side, so on the long wavelength or short, long wavelength or lower energy, lower frequency side of the spectrum. So this means if we go now back to the slide.
Can I ask one quick question? You have now a lack of energy if you compare the absorption energy and the fluorescence energy, and these are just ready. The other type of radiation is just the vibronic part of the spectrum you're losing there because you just mark the fluorescence part.
So yeah, you're
What's
right.
happening?
So in terms of energy, something is happening here because we have photons coming in with a certain energy, and we have photons leaving with less energy. So some energy must remain in the system. And this is what's dissipated here through collisions that reduce the vibrational energies or transmit translational vibrational energies among all the molecules in your liquid. And on the macroscopic side, this just means that your liquid will heat up. Right?
Okay, so there's no vibrational part in the spectrum left there. Then it's just heat. Okay, that's what.
This is a vibrational. This is a vibronic transition because it is a transition between some electronic excitation and vibrational excitation to some other electronic excitation with some vibrational component to it, right?
Okay, now it's clear.
Yeah, so it's just a mix. It's always a mix, but some part of the energy is missing. This is what's heating up your active system or your active medium, and this is actually a big problem because it will destroy your medium if you do not get this heat out of the system by cooling your active medium. This is easily done in terms of dye lasers because you can simply have your laser medium realized by a beam of liquid, and then there is always new liquid coming in, and you can cool the liquid efficiently. So this is why liquid-based dye systems are still popular. On the other hand, this is the liquid has some other disadvantages. It's a very messy thing. You know, if you have a problem with your lens, before I decided to become a theoretician, I also worked in a lab. I think in one of the labs over there is still a big puddle on the floor with some dye that left a stain. That's because of me when I was mixing some rhodamine dye. So it introduces some other problems, but it has this advantage that you can get the heat out in a crystal. It's not so easy. You have to think about how to effectively cool the crystal. Otherwise, you will destroy it. It will break.
So you always have to know the power of your laser and some kind of heat capacity of your medium to interpret the fluorescence spectrum correctly. Because if you don't know that, you can't interpret it.
Exactly. Yeah. This is so. This is correct, and a medium such as a solid object, a crystal, is typically not conducting very well. So then you have these heat centers, and you have changes in expansion, and this might simply break your brittle crystal, right? So this is an issue with solid state lasers, which you do not have with a liquid-based laser. Okay, so let me...
May I ask a question as well?
Yes. Mm-hmm.
What determines the lifetime of those vibronic states?
Mm-hmm.
These simple vibrational states in the excited states?
Yes.
What determines the lifetime of them?
Mm-hmm. So we'll get to this. It's a little bit related to line shapes in spectra, but obviously it has to do with how strongly your system or your single molecule is coupled somehow to the environment, because this is where you dissipate your energy into. And so it is about, so in a gas, this would be a function of pressure and temperature, for example, right? So this would introduce this would be the parameters that determine how quickly this process of relaxation and the loss happens. And in order to get to this population inversion that I talked about in as a fundamental concept in laser physics, you would like to have a situation where you have a a level in which you excite, which is sort of metastable, where you can pump your molecules into, meaning that you have excited this state, and this excited state often has a different spin multiplicity, for example, because this would permit a direct relaxation into the ground state. And so then you have a lot of these excited states. This molecule is, so to speak, trapped in this excited position, and there is only a few channels in which it can then relax through to the ground state by having population transfer from this metastable level to your laser level, and then from the laser level back to the ground state. So here you would have, ideally you would like to have a very long lifetime for this specific state in order to reach your situation of population inversion. Otherwise, if the excited state, and this is the problem in a two-state system, if you excite, the best thing that you can end up if you excite a two-level system is a 50-50 population in both states, because you will actively depopulate also your excited state through the incoming photons. You need this third level to park your excitation somewhere to build up and then have this inversion that we need here to have induced emission as the leading process. Okay, so I'm sharing my screen now with you again, and we'll go back to the slides. So you see the adsorption spectrum at a higher frequency or shorter wavelength in comparison to the fluorescence. Now with this picture, I just try to create in your mind using the board, you understand why the fluorescence is typically red shifted. Okay, lower left corner, you can see some of these dyes in fluorescent light. So you provide some spectrum in the blue or in the UV range, and then what you get back is this fluorescence, and you can see different dyes give you different colors because their maximum of fluorescence is at a different wavelength. You can play with one dye, changing certain ingredients when you do the mixture, when you make your when you're cooking up your recipe, basically. So it gives you some flexibility, but for certain classes or certain parts of the spectrum, as you can see here, you will use different dyes. So here you can see a list of typical dyes and the corresponding part of the spectrum which is covered by this dye. Okay, so let's see what I have here. Okay, this is one of the first laser systems we're going to discuss. I've also have a video for you to show you how this setup looks like. This is a dye laser, but it has a cuvette, so that means you have a piece of glass that is filled with your dye, and you use a pump laser to bring energy into your active medium, and your resonator, in this case, is realized in the following way. So this is one side of your Fabry-Perot interferometer, basically. This is a mirror that lets through a fraction of the light. You build up your standing wave between the two ends, but one of these ends here, in this so-called Litroff setup, is not a mirror, but it is a lattice. So we have a lattice here as a wavelength selective element, and use it as one of the reflecting planes in our laser setup. So this is one end, this is the other end, this is our active medium. So this is the dye sitting in this piece of glass. And here you can see a few other things. Here it says telescope. Why do you think is this a telescope? What makes it a telescope?
Because it concentrates parallel beams, so they meet not in infinity, but in a real distance, like in a real telescope.
Yes, that's correct. I'm just trying to link this back to very early lectures of experimental physics, for example, where we are talking about this type of setups. So just to brush up a little bit, what's the distance? If I give you the two focal length of the lens, what's the distance between the two lenses here?
It is exactly the focal length
Of
of the lens.
both. Yes, the sum of both, right? So f1 plus f2 is the distance between them, because you can see the incoming beam of light here is parallel to the outgoing, right? So they share the focal point. And what it does is it's widening up your beam so that you can get a lot of these slits of your lattice in light, increasing the resolution, as we heard. Remember, a few slides ago, we were talking about this equivalence between Fabry-Perot and a lattice-based interferometer, where we said your resolution gets better the more of the slits get actually get in contact with light. So this is what you do here. It also has a small Fabry-Perot etalon in between. So this is simply a glass plate, for example, to have yet another wavelength selective element. And this is how it's realized. One other thing is how is energy brought into the system. It's coming through a pump laser. We will see this in the video. In a moment, this is where the pump laser is coming in, hits this mirror, and then is coupled into the medium by focusing the beam of the pump laser onto your dye. The lens here has a cylindric shape because you want to have something like a lengthy focus point, not a point, but something extended in one direction, simply because this is the shape of your cuvette here, to bring as much as possible to reach or to excite a larger part of the dye that you are offering. What's the outcome? Look at this spectrum here, intensity as a function of the wavelength. We compare the fluorescence band of our dye that we have chosen. It's very broad at first. And then you can see what happens if you bring in the lattice and your wavelength selective. What happens is that your intensity, the width of this peak, narrows significantly, because you are now wavelength selective and you are removing the possibilities for other types of excitations in this molecule by only enforcing the population and excitation and relaxation of this specific electronically excited state that you use for your laser. And you can improve this even more so by adding yet another wavelength selective element, for example, here this etalon. And then you get not just a narrowing, but also a certain push. You get more intensity in this regime of very small variation in your wavelength. So this is where you want to go to be as monochromatic as possible. Right, then another setup here is a continuous dye. Oh, I forgot to say, so this is a pulse dye laser here, meaning that you come in with a laser source that brings in the energy for the excitation in your dye, but in a pulsed fashion, right? So this was the first way of how lasers were built. The alternative is to have a continuous use, where you just come in with a continuous source of light. Here, in this case, we are looking then at a laser of the company Coherent. It's a dye laser again, and it's interesting to see how this is realized. The medium in this case is a beam of liquid, and you cross this beam of liquid in a perpendicular angle in terms of, this is how the dye is like a jet is crossing the laser beam. And it's not a cylindric shape that you would like to have for your jet. Instead, you make it, you have a nozzle that forces the liquid to come out in some flattened shape so that you can create a certain angle and play with the angle between incoming light and the surface of your liquid, because you're going to hit for which angle? What's your guess?
Brewster angle.
The Brewster angle, right? We hit for the Brewster angle in order to avoid any reflection if we choose, or if our incoming light has some chosen polarization plane, right? So we'll cover this in a few minutes in greater detail. Okay, so before talking about line width, let's go and have a look at a few videos. Let's start with the pulse dye. So it's an ad, so therefore it's very okay. I'll switch this off. So here you can see. Let me go back a bit. Okay. So it's an ad, therefore this very nice music in the background, but we don't need it right now. So the setup is the following. Here we come in to this hole. We come in with our pump laser. This could be an argon ion laser, for example, or some solid state laser that offers a high intensity, but it doesn't have to have this ability to be tuned over a large portion of the spectrum, because you buy your pump laser in a way that it lies somewhere in your absorption spectrum of the medium that you're using. And if you have several different dyes, this might shift a little bit, but if you these pump lasers offer you a wavelength that typically suits many of these dyes, and you can use them to build then your own tunable system in a setup like this one. So we come in with a mirror here and then couple the light into our cuvette. So this is now this piece of glass filled with the dye. And let me forward a little bit. So here, this is the mirror where we couple out. So this is a partially transmissive mirror here. And on this side, this is not the mirror, but this is the lattice. And here with this screw, you can adjust the angle and therefore change your selectivity of wavelength by changing the angle on the lattice. So that's the setup. Now let's see how this looks when actually used. So here you can see is adjusting or tilting the lattice, and here you can see it's in a pulsed mode, and they are using a piece of this styropor plane here to show that it is basically emitting in a TEM mode 00. If I have prepared an extra slide, no, not an extra slide, an extra video where I'm talking a little bit about the possible TEM modes that can appear. It has to do with the shape of your active medium. It has basically 2 degrees of freedom. One is the radial part and the other one is the angular part. Explanation for this phenomenon that you have a certain structured intensity if you project this onto a screen is pretty simple. If you think about having the condition fulfilled for constructive interference in your resonator, also means that you might have constructive interference for something that is slightly tilted if the extra longer, the slightly longer way again fits and is a integer multiple of your wavelength, right? And this would also fit into the system. So you have a certain tendency to also see coherent light off your optical axis. And what you're trying to do is to adjust the whole system to get in this 00 mode. So this 0, 0 is just a sort of a set of reference numbers, like quantum numbers you use basically to describe the modes in which your standing wave inside the resonator can be oscillating. Okay, so let's continue, right? So here to show the diagram, and this would be a few pictures. If you darken the room, you can see the beam. I mean, if you have sufficient intensity, meaning you have energy over time and area in the line of your beam, you can even see this in broad daylight. It's just a matter of what's your photon density, because you always have certain dust grains and stuff in the atmosphere. And if the intensity is high enough, you can see the laser, like in a Star Trek movie, you can see then the laser even in daylight. This is especially true for the standing wave that builds up in the resonator, because here you have a much, much higher photon density in comparison to outside of the resonator. However, it is not a problem to put your hand inside the resonator into this lamp, because the moment you go into it, you immediately force the standing wave to collapse, because you stop the process of inversion immediately and nothing can happen. But if you put your hand in the laser outside of the coupling, what's happening outside and the loss of energy doesn't matter to the resonator itself. So it will just continue pumping energy, and this will then cause injuries, right? So that's something that's illustrated in the second video I'm going to show you. So this was a pulsed.
Sorry, I have a question there.
Sure.
I'm a bit surprised about the dye, that there is no problem with the uniformity of distribution of the dye inside the cuvette and sedimentation.
Mm-hmm.
Is that all? Because when you leave it a time, then sedimentation starts, and that will have its effect on their properties, isn't it?
Yeah, you're right. I mean, you have these effects, but so the laser dyes are made in a way, so this is a powder that is extremely well soluble in the liquids that you're using. This is like a mixture of glycol and some thinner alcohols. You mix this together, and it's indeed important how old your mixture actually is, because you have side effects by coupling in these photons where you also destroy the dye over time. And so this plays a role, and it has an effect on your intensity output. So this is a lot of experience that you need when you mix it and when you tune your system. And of course, as you say, you have also this aging phenomenon and the problem that you might have a certain gradient of concentration, I guess, in the dye itself through gravity if it's not stirred or anything. So this is these are all problems that can occur. It's less of a problem if you use the second type that I'm going to show you now.
I'm sorry, additional question to that. So it is not stirred normally, and there's no flow inside the cuvette. It's just a stable liquid in there.
Yes. Mm-hmm.
Okay. Thank you.
Yeah. So, right. So in this case, as you said, you just fill it with a hopefully perfectly mixed liquid, and then you use it for a certain time. And at some point you will have to replace it. The problem of this degradation or any tendencies of a gradient in concentration so is compensated in a setup where you are pumping the dye and you have a circulation. This is also very convenient in the sense of energy or heat dissipation, right? Because the liquid will heat up, but you can collect it on the other side. So you spray the dye through your pump laser and collect it on the other side. The only tricky thing is that you really hit with your dye into this collector, which is some sort of plastic funnel or so, where you have a certain circulation, and you can cool it in this circle as well. So this is a more convenient solution. And here you can see a system. Oh, again with music, right? So here you can see a tunable dye. Oh, is this the same video? Pulse dye, sorry, my mistake. CV laser, that's what we want to create. This is a device of the company Coherent, now pretty old 599 dye laser. It is a setup, a tabletop setup sitting in some laboratory, again pumped. So you can see there is a pump laser coming in here. So there's a slight hole. We are coming in, and this is the setup where the dye is sprayed basically into the beam and it's crossing your beam of light here somewhere. So this is where it comes. Then you have a nozzle where you blow it through, and here you have the funnel that collects it, and then you recirculate the liquid and cool it in this process. They have placed a power meter at the exit. Wait, let me stop probably here. So here you can see the power meter. It has a sensor which with which they measure the intensity. So we have energy per time and area, so we can approximate what's the output power of the system. And this is an important tool, because when you set up the laser, you have many screws for tuning. And if you look at the manuals of these devices, they have a certain routine, because this is a highly complicated nonlinear optimization. If you screw here, it might do something completely unexpected. So there is a certain series of steps that you're supposed to do in order to converge to the desired maximum output. And there are some tricks where you use certain reflections of the light and so on. So you have to know what you're doing in order to adjust the laser, and you get faster over time. So this is also a lot of experience that you need in setting up these tools. That's what they have done here, and you can see you can, to some extent, see the beam already in the resonator. It has this orange color. And let me see what they're doing next. So here you can see a setup where it becomes clear how the energy is transferred into our tunable system. So this big piece that's sitting here, this has can be maybe like 2 meters long. This is a gas-based pump laser that hits a mirror here and here, and you can see this laser has a significant output power. You can even in daylight see the actual laser beam going then into your tunable system. And also inside the dye laser, you can see inside the resonator, you have a sufficiently high photon density that you can actually see the tuned laser light. So right, so they by now changing. I don't think you can see it here in this video, but if they tune through the whole area that your fluorescence spectrum of your dye allows, you can see how the color changes. For example, from an orange to a green or something. So that's a very interesting thing to watch. Let's see what the guys here in this lab are doing next. Oh yeah, of course, they are playing. So you can see that's happening. That's what happens when you put a piece of paper in the pump laser because of its high output power. And my question for you, look at what's going on here. See this reflection? We have some interference here. What is going on? Can anybody tell me? Think back of the slides of the previous. meeting.
Maybe there's some resonating between the paper and the incoming beam because the paper is very white or something like that.
It has, of course, it has to do with the paper, but the reflection or the interference phenomenon that we are seeing is not something that is caused by the paper itself, but with something else. Where do we have this interference that creates this reflection? It's not on the device. This reflection is somewhere else.
In the camera, the lens of the camera.
Exactly, it's in the camera, yeah? So what's going on? What's your guess?
Yeah, the lens of the camera is focusing the beam. And so there are certain interference wavelengths which are causing an interference pattern in the detector.
Yeah, but the device that so the detector is, so we are the detector. The interference, the device, the optical device that causes the interference is a device that we have discussed a lot last time. It is simply a piece of glass, namely the glass of the camera. And what's the reason for this phenomenon to appear right in the moment when he's putting in a piece of paper? What kind of light source is he offering in this moment?
A diffusive one.
Yes, exactly. It's a diffusive point source, right? So we have monochromatic light, and this light is, lambda is fixed, but it's all from the same point in space, so therefore it's varied in angle. And for some of these angles, when hitting the glass front of the camera, you see constructive interference. And so we have a interference, a part of the interference pattern we would see in a Fabry-Perot interferometer, right? So this is what's going on here in the moment when he's putting this into the beam. Okay, right. So then let's stop here and go back to our slides. So we have been talking about laser systems. In this context, it makes also sense to speak about the actual width of the lines that we are going to see. So the thing with the laser is that it revolutionized molecular spectroscopy because of its very, very narrow width in the megahertz regime in terms of energy, right? So you can, in principle, reach now very, very good, very specific types of excitation. So your resolution should be good enough to see finest features of your materials, but there are certain caveats that we have to talk about right now. There are certain broadening mechanisms, right? So there is something that might make the interpretation of our spectra a little bit more complicated. And the first type of broadening we're going to discuss is the natural line width, related to the Heisenberg uncertainty relation, saying that we have a certain lifetime, tau or delta t, of some state. So it is an excited state that has a certain lifetime, meaning that after this lifetime, it will relaxate to its ground state. And this product of energy and time has to be larger than h bar. So you have this connection to the uncertainty in a sense that we will have a certain broadening, because if you have some delta t, you have a delta e, and this translates into a delta nu, a certain uncertainty with respect to energy, and therefore a slight broadening of your line simply out of the quantum nature of the system you're studying. This is most easily demonstrated or explained in a way as Demtröder does it. So this is from Laser Physics. You can read it up. It's on page 42, where Demtröder describes it through the picture of a damped harmonic oscillator. So you think of the electron in the field of the nucleus as a particle in a that is able to oscillate. So it's an oscillating electron hull. You think of the particle moving as over time, x as a function of t, and you assume a damped harmonic oscillation because we emit light. So there is some energy that is getting lost because it's emitted as a photon, and the simulation therefore is a damped harmonic oscillation. So this would be the differential equation in one dimension, and the solution of this differential equation is written here. As we all know, if we look at x as a function of t, it has this oscillating part typically, and it has an envelope function which is a decaying exponential function, right? So this is the solution for this type of differential equation. Now, what Demptruder does next is saying that for minimal damping, so if this gamma is much smaller than omega, we can make a slight simplification. We can remove or set the second term here to 0, and just take this part with the exponential and times the cosine of omega t. And now the oscillation amplitude, as you can see here in this image here, the oscillation amplitude is declining. And if you do a Fourier transform or a Fourier expansion of the signal, you will see that you will need more than just one frequency in order to get a get a pattern with a declining amplitude, right? So it might be, don't confuse the fact that, I mean, if you have a damped harmonic oscillation, you have a constant omega here, right? So the peaks are at equidistant. But if you would like to describe this type of signal through a linear combination of harmonic functions, you'll need many of them, right? So if you do the Fourier transform, or you write, what does it mean to do a Fourier expansion? We are expressing our solution x as a function of t in a basis of trigonometric functions, here written as e over I omega t, with some unknown prefactors a as a function of omega, right? So omega here as the angular velocity, 2 pi times nu. So this is something that we can do if this is this is a mathematically exact. This is a full or complete basis, so we can write x as a function of t as this function, and then put this or do an inversion, because what we're actually interested in is these coefficients here in our combination to form the solution, right? So if I take the inverse, so inversion, I'm getting the Fourier transform of x over t, which is then a over omega, is prefactor for the Fourier transform, and then integral over x of t times, and this is the factor that comes from the inverse Fourier transform. And now I'm taking for x of t my solution as we obtain it from the damped harmonic oscillator and put it in here. And then this expression that remains it can be integrated out. And with this, I obtain the amplitude as a function of omega. And by this, I'm getting right away the intensity of the emitted light, because the intensity is proportional to the square of the amplitude. So this is a function that you'll have to look up or put into Mathematica, or play a bit on a piece of paper yourself to solve this integral here, to obtain, after taking it squared, a value for the intensity as a function of the angular velocity omega, here written centered at some frequency omega naught. So this is what you obtain. And a last constraint that you put in is that you say that if you integrate over the intensity as a function of frequency, and you integrate over all possible frequencies, then this gives you your total intensity. And the total intensity is what you measure, like what we saw in the video when they use a power meter. They measure energy output over time in an area. This is an intensity, and so you can end up here with a so-called normalized profile, which is called the Lorentz profile. It is I omega over I naught. So this is with respect to the original intensity I naught. And you see that your intensity profile, intensity as a function of omega or as a function of nu, the wave, the frequency, has a typical shape, which is called the Lorentz profile. And when you calculate the natural line width, so the width of this type of profile, you end up, let me just quickly show you. So here, the red line, for example, would be a would be a Lorentzian profile. So this is how a line, a naturally broadened line would look like, intensity as a function of frequency. So that's what you get for this type of natural broadening, simply through the fact that we can describe the emission of a photon as a damped harmonic oscillation process. And one last step we have to make. So this is how we end up with our formula for the Lorentz profile. But to link it now to the lifetime of a state, we have to do one more thing. This is also still taken from Demtröder, so you can read it up in this book, Laser Physics. So what he's doing next is the following. He's still with our damped oscillator approximation, but has multiplied the differential equation on both sides with the derivative of x of t. So it's in Newtonian nomenclature x with a dot on top. And by doing this, you can pull out a full time derivative, because if you take the derivative of m over 2 times x dot squared, you get 2 times m over 2 times x dot times, and then the inner derivative x double dot, right? So this is what you can do, and immediately you can see what this time derivative actually is. dt of m x dot squared half plus m omega naught squared half times x squared. What's this expression here? Just to check if you're still with me here.
Which expression, please? No.
In the brackets, so where we take
The whole.
Energy.
Yes, it's the total energy, exactly. It's kinetic energy plus the energy in our harmonic oscillator, because m, you can write this m omega naught squared as d, as your constant, as your spring constant, basically, kx squared over 2, right? So this gives you a change. This is W stands for work, could be an E, but sometimes the E is avoided because it might be confused with E as electric field vector. So here they write W as the energy, here the W over dt, and on the right hand side remains the term that is related to the damping, right? Now we put in the solution of the previous page. So this was the solution, the simple solution for the damped harmonic oscillator, which has this exponential part times the sine. But here, note, it is the derivative with respect to time and then squared. So this is why we have the sine squared appearing here. And if you take now the average of the change of energy over time, so change of energy over time is dW over dt. We take the average, then sine squared averages out, and you have this expression here that remains. And all that you have to remember now is the following, that you see that the radiated intensity, which is proportional to what you are having here, to this change of energy over time, is drops to a value of 1 over E in a time tau, which is 1 over gamma. Because if T is 1 over gamma, then you have e to the minus 1, and you have reduced your energy to an nth of the original amount, right? So you can see that the larger your gamma, the smaller is your time tau until you have reached only half of the intensity, right? And so we see this is what connects lifetime to this damping in our ansatz through the harmonic oscillator with a damping term. So the higher the damping, the shorter is the lifetime. Or in other words, if you look, let's go back. So this would be a very small a damping. So gamma is pretty small, meaning that in this case, your tau, your lifetime is pretty high, and your broadening will be less than in a case where you have a very strong damping and a very short lifetime, right? So this connects the lifetime of a state after excitation to the actual width of the line when you look at it with your spectrometer. However, this is only relevant in a condition where you have where your device that you're using offers sufficient resolution to actually see this broadening of the line, because there are other phenomena that are much, much more affecting the actual width. And this is what we're going to discuss on the next few slides. What's written down here is just that if you have a state, if you have an excitation from some lower level, this is often denoted as I, as initial level. So here you can see the index I means initial, and then often they say F for final, but sometimes they also just continue in the alphabet, skipping the J and going to K. So K is then the upper state level, and both of them have some lifetime tau. So you have a tau I and a tau K, and the width depends then on both, and you can see how the uncertainties add up, because you have a 1 over tau K, so the lifespan of the upper state inverted, and here the lifespan of the ground state or initial state inverted, and this in sum gives you the broadening. You can see that the smaller the lifespans are in either the ground state or the excited states, the broader your line for this type of excitation from I to K will be.
May I ask something to the original premise of this damped harmonic oscillator? What is X then in our interpretation? This variable that we use. How do I relate this back to this two-niveau system where we have some energy outcoupling via the radiation?
Yes. So it is a simplified picture in our mind where we think of it as the electron, for example, moving in this one-dimensional fashion over time, right? And so it's actually the whole electron hull that has an oscillating movement that you are mapping basically on a one-dimensional oscillator. You say this varies in time along some axis as x over t. And this oscillation that is caused by some incoming light. For example, when a photon comes in, you have the wave passing by, you modulate, and you have this resonant behavior of the electron hull. But you also couple out then energy by emitting photons, and this is implemented in this picture as something that dampens this oscillation. So it goes back to a state where it is less oscillating, because in the end it is still in some electronic state, right? It is in some we can't think of it as a static object, but it is, to answer your question, a mapping of the actual oscillation of the electron hull onto a one-dimensional oscillator.
The electron hull, what do you mean with that?
I mean the Yeah, maybe the valence electron area of your atom, because innermost electrons are not so affected. They are affected only by photons with sufficient energy to even create a shaking of the system that affects these inner electrons, which are much more strongly bound to the core. So typically you have the valence area. If you think of an alkali atom, you have this electron in your S-type shell. And this is the making a certain oscillating motion that is then damped because you are emitting electromagnetic energy over time. And in this model description, it appears as a damping term when you describe the motion of your electron density in this one-dimensional picture.
But this is just, it's a description where the radiation or the emission just appears as the outcoupling process,
yes,
or the energy providing process, not the motion is, because in this one picture with the two niveaus of our system, there I don't really have this oscillation of my electron.
Yeah, this is a good point. And I think, of course I wanted to do 10 more slides, than what we can do, but let's talk about this a bit more, because I noticed in conversations that this is a little tricky. When I draw this picture of niveaus or levels in a system, it makes sense, and it's sort of intuitive to think of an electron jumping from one state into the other state, right? So it's like lifting something somewhere up. It's natural to our understanding, like in the field of gravitation, you put something up, it has a higher energy. So it's kind of, but what it means is that you are changing the electron density distribution in some way. And when you do the electronic excitation, you can think of it as like a standing wave. It's also not fully correct, but this was the first picture in the postulates of Bohr. When you think of having your matter wavelength through the de Broglie relation mapped onto your orbit, right? This is a simple picture. It is wrong because it's a one-dimensional. Now, if you solve the Schrödinger equation, you see in order to make this all work, your electron density distribution has to be way more complicated. It has this radial dependence, which is described by the Laguerre polynomials, and it has this angular dependence described by the spherical harmonics. And this is how your your electron density is distributed. And it's differently distributed in one state than it is in another. So if you have a change from one level to the other, it means that your electron density is really completely differently arranged. And between these two states in the transition, you have some sort of oscillation that goes on, right? It's a perturbation. The whole thing does something and relaxes till it finds this other quantum state the system can relax into. And this process from here to there is here described as a damped oscillation where we get rid of some energy because we're sending out a photon. So it is a trick. It is a way of thinking about a process that it's hard to imagine, and it's simplified in the sense that I think of it as a one-dimensional oscillator where the loss of energy through the photon is approximately described through a damping term.
Sorry, I have another question to that. I can just jump in there. What is then the interpretation of the damping? Because when you have certain energy levels which are allowed, and a damping is a loss of energy, right? So then it has to jump down to another level. There are no in-between steps where you can have a continuous damping like in an oscillator. So what is the interpretation of the damping? Because you have, in my understanding, you have just the upper level and then it jumps down and then you have another level, and the energy which has to be radiated is always this energy distance between the two levels. But how can you have then first the total energy and then damping down to like half of the energy?
No, but the line that you see in the spectrum is the difference between the two states, and this difference is broadened.
Yeah, but when it's broad, then there are also oscillations or also, how can I say, energies which are not exactly this energy gap between the upper level and the lower level. Otherwise, it would be a perfect line, wouldn't it?
May I offer a solution? And that is, don't forget the fine structure. And I think this is applicable also to that we actually don't have those fixed, we think of it as the fixed vibrational level, but there are that many levels that they appear sometimes as nearly continuous. Could be an answer to that?
This is another thing, but it has nothing to do with the actual natural line width, which is a fact that is most, I think it's most clearly seen if we go back to the slide 28, because obviously in this damping harmonic oscillation, there is only one omega here, right? In this oscillation, that the actual motion in this picture x as a function of t, and only if you do a Fourier transform. So if you try to describe the signal that you get, because the signal is declining, okay, so it's declining over time because of this energy sent out in the process of emitting the photon. You have in the Fourier transform not just one frequency, but a certain broadening, because you're doing a combination. Sorry.
Because the photon itself hasn't a zero width, but is basically a Gaussian pulse. A photon itself can't be zero in time.
It is in this picture.
Basically, the solution.
I think in this picture it is that if you look at x as a function of t, you have a decline of your amplitude over time. And in order to describe this phenomenon of a declining amplitude over time in this oscillation, you simply have you have in a Fourier transform picture several frequencies that are necessary to describe this time phenomenon. So it is the phenomenon of a declining amplitude over time that creates a certain width in the Fourier space after transforming from time domain into frequency domain. I'll think about it myself. Maybe there's a better way of explaining it, but that would be my way of referring to the effect that we're discussing here.
Sorry, may I ask another question? So when we do absorption spectroscopy, there is those we measure the response of molecules over a spectrum. And are the absorption lines in absorption spectroscopy also broadened according to this?
Yes.
So then it's basically the inverse of absorption spectroscopy, isn't it? Because in absorption spectroscopy, we absorb light. And because it's not just that line width, we have the broadening. And the inverse of it would be we emit light, but we cannot emit light at a single line width. We have a broadening of the spectrum.
So it doesn't matter if you do it in adsorption or in a transmission. So if it is a relaxation or an adsorption process, it depends on how you set up the detector. You can provide a certain continuous spectrum and then check which type of the spectrum has been lost, what has been absorbed, basically, right? And then you would see this phenomenon of a broadening in this way, or the other way around, if it is the light that's directly coming from this object through the emission, but it's the same phenomenon of a natural line width. So it is just one or the other. It is, the explanation in both ways, because for the excitation from initial to the final level, or for the de-excitation from the final to the initial level, you will have this broadening phenomenon in which both lifespans of both states will go into in the very same way.